Hello everyone. This is the third video in our lecture series about introductory Python. In this series, if you're following along on eClass, all of these slides are in lecture number 3. However, just to shorten this up a little bit, I'm going to do this as a series of 3 separate videos. So there's going to be a 3A and a 3B and a 3C, as you'll see. So let's just get started. All right, well, in the first of this 3-part award-winning lecture series on data structures, I'd like to start here with lists and dictionaries, and we'll do a little bit of command line work, a little bit of coding work here at the end in the Python interpreter to play with those. In the second video, I'll move on to some more uncommon but really useful data structures like sets and tuples. I'll also do some other odds and ends like the in and not in operators and some brackets, things like that. And then in the third one, I want to spend a little bit of time talking about two-dimensional data structures. These are really, really crucial. As I mentioned, anytime we bring data into a Python program, we have to create a data container for it. If we're modeling something in the real world that's complex, 2D data structure is sometimes the best thing to do. So we'll talk about that in a separate lecture video. But for now, I'd like to start with lists and to talk about a technique that we can do with lists called slicing. So as you've seen, we've already talked a little bit about variables, and we have these two metaphors for data containers. The first one we've already talked about is a bucket. Sometimes we call this scalar variables, but Python doesn't use that term that often. But we can put anything we want in there. We've put numbers in there. We put strings in there. Later we'll put other things into a bucket. It's totally fine. Today, though, I want to talk about collections of data, or sometimes you could think about it as plural data. And the metaphor that I want to use for these is a filing cabinet. And the filing cabinet can have as many drawers as we want to. It could fill up our entire computer memory if we wanted to, and that's totally fine. Every drawer works a bit like a bucket. It can contain either 0 things or 1 thing. But the name of my variable will refer to the entire filing cabinet. There are basically 4 of these in Python that I think are really important that I want to talk about. This lecture is going to be the list and the dictionary again, and then the next one we'll look at sets and tuples. So if I wanted to take, for example, these first 8 letters of the alphabet, and I wanted to put them into a kind of a collection or a plural data structure, the bucket obviously isn't the best case for me here. So I'm going to use my metaphorical filing cabinet, and I'm going to put these into a filing cabinet, and each one of these letters will go into a new drawer in the filing cabinet. I can create as many drawers as I want to. In this case, I only need 8. So each individual letter is going to be called a value when I put it back into the drawer. But what's interesting about this filing cabinet is that the drawer has a label, and that label is going to be a number. We call those numbers indexes. And what's interesting about the indexes is that we start counting from 0. So these 8 drawers in this list are going to be numbered 0 through 7. And we always start counting at 0. And in fact, in class I have this mantra, this little gig, and I come in, I'm like, hey, indexes start counting at, and everybody yells out 0. And you can do that at home on your own time. But this is what's pretty crucial about this. We always start counting at 0. One of the metaphors that I heard about this once makes some sense. So imagine a garden path, and there are just stones in the garden path. Maybe they have letters on them, A, B, C, D, right? And the index is the number of steps you have taken down the garden path. So if you're starting at the beginning and you're standing on stone A, you have taken 0 steps. But if you go to B, you have taken 1 step. And this is actually not unlike what really happens in the computer under the hood, because the indexes are really an offset. So the first letter, A, has an offset of 0. We have to advance 0 squares to get to A, right? So this is a really crucial component to remember about lists. They're organized sequentially, they are numbered, and those numbers always start at 0. Here's a really simple way to make a list. We will see more as we go along. Lists are so convenient and so handy that there are multiple ways to make them, but here's an easy way to get started. Here I'm going to make a filing cabinet called letters, and I'm going to put all of these letters A through H into that filing cabinet. The square brackets tell Python that I would like to make a list, and the strings here, A through H, are the individual elements or data values that I would like to put into those drawers. So Python will automatically create one drawer for each one of these elements. Python will automatically number them as well. So I don't need to tell Python A goes in the 0th drawer, B goes in the 1th drawer, 2th drawer, right? So this is also one of my jokes, right? Is that I count these in a goofy way because it helps us remember that the first drawer, that's a little ambiguous. When he asks me what the contents of the first drawer are, is he really asking for B or would he be asking for A? So I make up this goofy thing about counting. So this is the 0th drawer and the 1th drawer and the 2th drawer and the 3rd drawer. Now, that's not actually how we count, but anybody who tunes into this video later and doesn't know my joke, it's going to, anyway. So the square brackets then are the way that we signify to Python that we're making a list. And that's really, really, really important. And by the third video, I'm going to show you all of the different kinds of brackets, and you're just simply going to have to memorize them. So for now, write this down on a Post-it note. Square brackets mean a list, and then just, stick that on your forehead for a while. So again, square brackets mean a list. The individual elements, Python will build a drawer for them. Python will number them automatically, and those numbers always start at 0. And one of the cool things about lists is that sometimes we need to go backwards. We need to go the other way. So as we've already seen, Python starts at 0, 1th, 2th, 3rd, all of the way up. But if I wanted to go backwards through the list, Python lets me count backwards as well. And in this case, I can start from -1 or -2 or -3. So you'll notice that when I go backwards, all of these numbers are negative. The -1th element of any list is always the last element of the list. Now, this is an important thing to recognize. Notice that that one isn't 0. And if it were 0, we would have a problem, wouldn't we? Because if that were the case, 0 could refer both potentially to the A drawer or the H drawer. It could be the first drawer in the list or even the last drawer in the list. So this is a pretty crucial component to recognize, which is there is one and only one element in a list that has the index 0, and that's the very first one. But counting backwards is really terrific. It's a great thing to do. This is a really convenient thing that Python's done for us. All right. So just as a quick summary, lists have these properties. A list can have any number of drawers, that is to say, any number of elements, even 0. And we'll see some occasions for this in the future as we go through, where we might be filtering some data or collecting some things that fulfill a set of criteria for us. And at the beginning of our process, we might not have any elements at all. So we might want to create an empty list or an empty filing cabinet that has no drawers, and then add elements to it as we go through. That's totally fine. Every drawer is a little bit like a bucket in that it can contain either 0 things or it can contain 1 thing. It's either empty or it's full. The drawers of a list always stay in the same order. And it's easier to remember that because each drawer's label is actually a number. Now we call that number an index, but those indexes go sequentially. And so because they're numbered 0, 1, 2, 3, 4, 5, it's easier to remember that a list keeps the drawers in the same order. And that's pretty important. The other really important fact about a list is that the drawers are always numbered starting with 0. And again, technically, that's because the index number is an offset. It's like how many steps have we taken down the garden path, right? Now, a drawer together with its index or its label on the front and its value inside, we sometimes call those an element. So one element is the drawer. It's both its label and its contents. All right. I can refer to any drawer in the filing cabinet by putting its index number inside square brackets. So if this is the list that I have created, I can refer to the 1th element, that is to say B, by putting the name of the variable, that is to say letters, and then no space, and inside a square bracket, put the index number itself. So what I'm referring to here is the whole filing cabinet called letters, but I want to look in the 1th drawer and extract that value. And that's what I'm getting when I refer to letters 1. I can refer the same letters 2 points me to the 2th drawer. Letters 5 points me to the 5th drawer. Letter 7 points me to the 7th drawer. And you may have guessed already, if I go to letters -1, I also arrive at the 7th drawer. But I can use these now and manipulate these in a variety of different ways. So for example, I could concatenate together a list of letters. I could say my friend's initials are whatever is in the 3rd drawer. Oh gosh, that's too much. So it's going to be D plus the 1st drawer, which is going to be B, which is the 2nd drawer, which is going to be C. So I could actually extract values from that list individually and work with them. I can also assign new values to those indexes, to those drawer elements, because I can put that on the left-hand side. So I could assign a new letter into the 3rd drawer, for example, if I wanted to. Right? That's totally fine. Python has a really cool thing that we can do. This is called slicing a list. This happens all the time. And Python is really handy for us. It makes it very, 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 very easy to do this. What I need to do is I can refer to my variable here. I'll just see the same one, letters. But inside the square brackets, where I would normally put the index, I can actually put 3 values in there. A start value, a stop value, and a step value. Oh, this is pretty cool because if I don't give it any data, then the start will start at 0 at the beginning of the list. If I don't tell it where to stop in the list, it will go all the way to the end. Otherwise, it'll stop before it gets that index. And if I don't tell it the step, it'll go 1 by 1 by 1 by 1. And what that means is I can extract parts of a list starting at a different place in the list, stopping at a different part of the list, and stepping through. Maybe I want to go 1 by 1. Maybe I want to go every other drawer. Maybe I want to go every 3rd drawer. All these things are possible with this start, stop, step syntax. And you'll notice the crucial part about this is the colon. So let's work through a couple of examples. I think it helps to see the examples, and that makes slicing a little bit more immediate, right? Now, here's a case where I'm just referring to the 2th drawer in letters. So that's index number 2, and we'll notice, right, that's the letter C. And this is the classic way we've just learned in order to refer to any drawer in a list. There are no colons in there at all. So this is just a simple index. It says, please give me drawer number 2. The contents of drawer number 2 is the letter C, right? But let's look at this one. So this is letters 3:6. Remember, start, stop, step. So here it says, I want to start at index number 3, and I want you to stop just before you get to index 6. And there's no step. So therefore I'm going to go one by one by one. So I get indexes 3 and 4 and 5. So in this case, what I get is a tiny new list of 3 elements that starts D and E and F. I am slicing from element 3 up to but not including element 6, one at a time. Here's another example. So letters 1, colon, colon, 2. Remember, start, stop, step. So what I'm asking for now is I want a slice of the letters list that starts at element 1 and it's missing a stop, so therefore go all the way to the end of the list, but it has a step of 2. So I start at element 1, I take every second element all the way to the end of the list. That gives me 1 and 3 and 5 and 7, or B and D and F and H. Here's one where the start is missing. Start, stop, step. The start is missing, so therefore I will start at the beginning, which is index 0. The stop is missing, so therefore I will go all the way to the end of the list. But the step is 3, so I'll take every third index. You can even do the math really quickly if you want. That's going to be 0, 3, 6, 9. 9 fell off the end of the list, so we don't have a 9. So I'm going to take 0 and 3 and 6, which is A and D and G. Here's one where I have a start of 3, and I'm missing a stop, so therefore my stop goes all the way to the end of the list, and I have no step, so therefore my step is 1 by 1 by 1 by 1. So I'm taking elements 3 all the way to the end of the list, in this case 3 through 7. Here's a goofy one. I just put this in here because you may see this occasionally. Here's one where I'm slicing letters. The start is missing, and the stop is missing, and so is the step. So I'm basically taking everything. I'm starting at the beginning, and I'm going all the way through to the end. This is something you'll see quite commonly in Python, and I'll just say if you wanted to know more about why they do this, check out Head First Python. But in the video here, I will tell you why this happens, and it will make more sense for those of you who have worked in object-oriented coding, which is I'm cloning or copying this list. I'm making a complete copy of it. I'm just kind of duplicating the object of the list itself and making a copy of it. And footnote, this is just a convenient, simple way, a Pythonic way to create a copy of a list. That's more common than you might think in Python. Now, slicing is so crucial, and I spent a little bit of time on that, and I hope you practice it in the Python interpreter or someplace, because it's a really convenient, crucial thing that we get to do in Python, and it's one of the reasons why Python becomes really, really popular, because this notion of slicing is easy and convenient and useful. What's cool about Python is that Python lets us do it with strings also. Now, we've already talked about strings. We said that a string is like a scalar variable, right? It's just like one thing. It is an entity. Here, I've created a variable called city, and I've put into city a string called Edmonton. And city is a scalar variable. It doesn't really have drawers. However, Python says, I know one of the things you want to do. You want to slice the string just like it were a list. And this is useful in text analysis and cryptography and all kinds of places we do this. And if you've come from other languages, you've probably seen in that language where we convert a scalar string into a list so that we can work with it, and then we have to convert the list back into a string. Well, in Python, We don't have to. So what Python says is, I am going to allow you to slice a string in the same way you would slice it if it were a list. It isn't a list, but I'm going to let you pretend like it's a list so that you can pull stuff out, right? So, for example, if I slice the contents of the bucket called city, remember, start, stop, step. So I'm going to start at the 1th element of the list. I'm going to start at the 1th element, the 1th letter in that string, and I'm going to stop just before I get to the 5th element of that string. That there's elements 1 and 2 and 3 and 4, or that is to say the string DMON. Right? Is city : 2, a similar structure. Start is empty, so therefore I will start at the beginning of the string. Stop is empty, so therefore I will continue to the very end of the string. But step is 2, so that means I'm going to take every other letter, right? So I'm going to take 0 and 2 and 4 and 6, or E and M and N and O. And what I get is a string. I started with a string, I slice a string, I get a string. We can do things like pulling the last letter off of a word by just referring to the -1th element. There are all kinds of reasons we might want to do this. There's tons of word games where we need to do this, like crossword puzzles and all kinds of things. There's a number of different applications for this. But a really easy way to get the last letter is to just extract or slice the -1th element. Similarly, you can always get the first letter of a string by looking at the 0th element, right? Here's the last one, city : 2::3, start, stop, step. So my start is at 2. My stop goes all the way to the end because it's missing, and I'm taking every 3rd element. So I'm taking 2 and 5, or M and T, right? It's perfect. Now, quick little footnote for those of you who have come from another language, especially if you've done some object-oriented programming, you can probably already see what's happening here. That both strings and lists are classes that inherit from a parent class called sequence. And sequence defines this behavior of slicing. And so because both strings and lists inherit from sequence, therefore they're both sliceable. All right. Well, let's move on to dictionaries, and then we'll get into the terminal here, and we'll just do a little experimenting with some slicing and some lists and some dictionaries. Dictionaries are a really close sibling to lists. They're so close, they're almost twins, with some crucial differences. The major difference between a list and a dictionary is that a dictionary has drawer labels that are strings and not numbers. The contents are still called values, but now in a dictionary we call those labels keys. Any drawer that contains both its label and its value, its key and its value, still make an element. But sometimes we refer to these, you'll see these referred to quite often in data structures, different kinds of data structures, especially if you're pulling stuff off the web, as key-value pairs. And in Python, that key-value pair creates a data structure called a dictionary. This is an interesting word to use. Other languages call them different things, like Perl and Ruby call them hashes, for example. If you know data structures, you'll know why that makes sense, but that's why I don't want to go down that path. PHP calls them associative arrays, but Python calls them dictionaries. And I think that label, that name is appropriate because it's a way that we can think about mapping words to other words. And that's what a dictionary does, right? We look up a word like, I don't know, banana, and then the dictionary will tell us with other words what that thing means. So a dictionary is kind of an appropriate model for this sort of data structure. Now, I said that these are kind of like siblings, and that's really true, but it's really, really important to remember what the differences are between a list and a dictionary. So here's what's up. Dictionaries, like a list, can have any number of drawers, even 0. They're filing cabinets just the same way that lists are. Every drawer, just like a list, a dictionary drawer can contain either 0 things or 1 thing. But here's the stick. The drawers are not necessarily guaranteed to stay in the same order. And what that means is that we give Python permission under the hood to reorganize the dictionary in a way that makes sense for Python. And that's okay. There are some consequences to that are actually really beneficial for us. We won't see those necessarily today, but we're going to see them in a little coding experiment in a couple of lectures. And then each drawer has a label, but whereas a list is labeled with numbers, a dictionary is labeled with strings. And we call that string label a key. And a key and a value still make an element. Right? So I'm going to give you 2 examples here. And I'll do the first one as and really literally as a dictionary. I know we all took Latin, but let's just, bear with me. This is okay. So let's imagine that we're building an English to Latin dictionary. And so the way that we want this to work is the label on the drawer is going to be an English word. And when we open the drawer and look inside, we will see the Latin translation of that word. So if you look at my little diagram here with the green boxes, you can see that the keys are tree and bird and wine and truth. Those are going to be the labels on the drawer, or the keys. When I open the drawer, what I will see is arbor, or avem, or vidum, or veritas. Right? Here in the code, this is how I actually create it. So notice that when I build a dictionary, I'm using curly braces, not square braces. Write that down on another post-it note and stick that to your forehead as well. This is crucial. We have to memorize it. Dictionaries use square braces. Curly brackets mean a dictionary. They're different. We have to remember that. So you'll notice that inside the curly braces here are a comma-separated list of key value pairs. That is to say, there's a key, which is a string, followed by a colon, followed by a value. Now in this case, all the values happen to be strings, but that doesn't matter. So tree colon arbor creates an element or a drawer in that dictionary. Tree is the label that goes on the front. Arbor is the value that goes inside the drawer. And there's a comma. New drawer. The key is bird. That goes on the front. Avem is the Latin word that goes inside. Wine is the key that goes on the front of the drawer. Vinum is the word that goes inside the drawer, right? Et cetera, et cetera, et cetera. All right. When I refer to any individual drawer, I kind of do it the same way I did with a list. And I'll acknowledge this may be a little confusing because now we're back to square brackets again. But Python is consistent in this regard. Anytime I access the drawer of a kind of a collective data structure, doesn't matter whether it's a list or whether it's a dictionary, anytime I access one drawer, I'm always using square brackets, always. In this case, the name of my structure, the name of my filing cabinet is English to Latin, and I want to refer to the contents of the drawer that has the label tree. So tree is a string. So Python will go and it will look at that filing cabinet and it will find out which drawer has the label tree, and it will extract for me the contents, which is the word arbor. The same at the end with truth. If I wanted to know what the Latin word for truth is, I go to my dictionary, I tell my dictionary I want the contents of the drawer labeled truth, and Python will return to me the word veritas. Now here's what's important about this. When we're referring to a dictionary or we're getting stuff out of a dictionary, we're almost always looking for the contents of specific drawers. And because we're doing that, Python is free under the hood to reorganize the dictionary in a way that makes sense to it. Consequently, one of the one of the implications of this is that it doesn't really mean anything to slice a dictionary, right? So my keys here are not in any kind of order, just the order I built them, like tree, bird, wine, truth. That's not alphabetical order. That's not in terms of the length of the word. It's not in terms of how common the word are. There's no organizational principle there at all. So it doesn't really make sense to say to Python, I would like to slice this from tree to wine. And because Python can reorganize that under the hood, there's no guarantee that we're going to get out exactly what we think. So with dictionaries, there is no slicing, right? Now we can do things with the dictionary. We can pull words out. We can filter it. We can do all kinds of things. There's a different technique for that, and we're going to see that in a little bit. Look at, a few more years, look at do comprehensions, right? All right. Here's a second example of a dictionary, and this is maybe one that's more common. I can collect information on objects in the real world, and those objects in the real world have properties or principles or attributes, right? So for example, here's a person. My person has these following kinds of qualities or characteristics or attributes. My person has a first name, my person has a last name, my person has a date of birth, has a date of death, and they have a citizenship. 5 components, 5 attributes, 5 characteristics, 5 qualities. So a dictionary is the perfect data structure to capture all of this. So their first name is William, the last name is Shakespeare, their birth is 1564, death is 1616, right? Citizenship English. And you'll notice that I can put any kind of data into the drawer that I want to. It doesn't matter. Some of these are strings, some of these are numbers. Does Python care? Nope, not one bit. And so what I can do is I can create a data structure like this, like a dictionary, and I can capture information about people. And I can work with that information. I can start to compare people. I can do all kinds of really interesting things about that, right? So each of these key value pairs creates a new drawer in a dictionary here called person. The keys are first, last, birth, death, citizenship. And the values are the contents of those drawers, right? Namely, William, Shakespeare, 1564, 1616, English, right? This is probably a more common use for a dictionary. It's one that you see all the time. All right. So that's it for the theory part about it. Let's jump over to the interpretive shell, and let's just do a little work with some of these structures. All right, well, here's a terminal window that I've opened, and I'm just going to drop into Python, into the interpretive shell, so that we can play a little bit with lists and dictionaries and things like that. If this doesn't make any sense, go back, look at one of the earlier videos or look in the DH Lab stuff, and you can get more info about how to do this. I have already put together a little list of friends. Who are these people? I have no idea. I made up these names. No clue whatsoever. But you can ask Python, no, I can't spell that, who the friends are, and you can see that we've captured that data structure. It is a list because it has square brackets, and we know already that this is going to get indexed from 0, 1, 2, 3, 4. So if I ask what any one of the friends is, who's in the third drawer, right? That's going to be the 4th person in the list. That happens to be Phoebe. So I can access any of these if I wanted to access who friends 0 happens to be. That's Ross. If I want friends -1, remember that's going to give me the person at the end of the list. That's Rachel. And you'll notice that there might be one missing. So what I'd like to do is I'd like to add that person now. And there are 2 ways that I can do that. One of the things is I can count. I can say 0, 1, 2, 3, 4. So they will go in the 5th drawer. So I could actually say friends 5 is so-and-so and so-and-so, but I'm not going to do that. I'm going to do something slightly different, and I'm going to append to the end of the list. So this is what we call a function or a method. More precisely, it's going to be a method. The data structure friends as a list knows how to add things to the end. and so we call an append method, and I send it a new element called Joey, and you'll notice that that is appended now to the end. I can ask how many friends there happen to be, and there happen to be 6 of them. So this function of len measures the length of that list. Interestingly enough, it also measures the length of strings. And as we saw a little bit earlier in that slideshow, Python has this cool thing under the hood where strings and lists, even though they're maybe technically not the same thing, get treated as really similar things. So sometimes what we learn about a list or what we learn about a string applies to the other one, right, which is great. All right, let me show you a couple of other things. Let's imagine, they're hanging out, but somewhere Joey has to leave. He was the last one in, and he's got to leave. So what I can do is I can pop him off the list. It returns to me that says that that's Joey. But if I ask now who friends are, you'll notice that Joey is actually missing, right? And that's okay. Oh, the kind of dynamic here, I will say this even though, is push and pop. So if I add something to the end of the list, I'm pushing. And if I take something off the end of the list, I'm popping. So this idea of push and pop are really common. I got to have a little quibble here with Python because I think the pushing should be called push, but it isn't. It's called append. So in Python, we're appending to the end of the list. So it's append and pop, append and pop. Append puts something on the end of the list. Pop takes something on the end of the list. I can actually do something too. I can pop anywhere, actually. So if I want to pop the 0th element, I can do that. And that'll tell me that there are 4 friends left, right? Which is pretty interesting. I can ask questions of it now too, like, is Joey in Friends? No. Joey's not in Friends anymore because we removed him, right? So I can ask something else like Chandler in Friends, true, because Chandler's still in that list. I can do this negatively, in other words, too. By the way, I'm just using the up arrow as a way to scroll through my previous commands, and I'm going to use the arrow keys to mouse over, and I'm going to insert not, and I'm going to hit return. Is Joey not in Friends? That happens to be true, right? So what we've seen, we saw this a little bit in our conditionals, and we're going to see it a little bit here in on one of the other slideshows, is that this in property, this in quality, is actually a Boolean, and it decides whether Chandler or Joey are in the list called friends. I can use the not keyword in order to flip that or to invert that if I really wanted to. Right, which I can do. 2 other quick things about a list here. One is lists actually know how to sort themselves. So if I tell the list of friends to sort themselves, and then I say, who are you? We're in alphabetical order already. Crikey. Okay, well, that doesn't really... I'm going to... that was a totally wasted bit of thing. Okay, never mind. I'm going to reverse the list, and now they're in reverse alphabetical order. So I can pick a better example. I can sort things if I need to, which is totally fine, and then I can reverse them, and I can manipulate lists like this. And again, this is really important, interesting. The feature that makes this possible is that a list is an ordered sequence because those indexes are numbers and those numbers go in a particular order. And so it has a sequence that is stable unless I change it by sorting or reversing or doing something like that. But the list of friends are now going to stay in the same order. But if I ask now who friends 0 happens to be, it's Rachel. So this is a crucial property too. We're going to see this in a little bit. When I change the order of a list, the indexes still stay the same, 0, 1, 2, 3, 4, etc., etc., etc. But the contents of the drawers, that is to say, the values, shift. All right, a little start over here. I'm still in the Python shell. I have taken the liberty to produce a dictionary, which I'm just going to paste here. And you'll notice in the Python interpretive shell that I get what we call a second line prompt. That is to say, this ... That means that Python knows that I'm not finished yet. How does it know I'm not finished? Well, as I'm creating my dictionary, I have an opening curly brace, and Python knows that this data structure of a dictionary will go until it gets the closing curly brace, and it hasn't seen one yet. So it gives me very politely and kindly a second line prompt of ... And then you'll notice as soon as it sees that closing curly brace, it says, oh, got it. I know what that data structure is. I can build that for you. And here it is. It doesn't display that quite maybe as prettily as the one that I put in, but that's okay. But I can ask this the same thing. So, person last, if I could spell last, that would be great. Shakespeare, person, I'm not going to say citizenship. Let's do birth. I'm going to stick with things I can type. Birth is 1564. So it's the same thing. This is metaphorically a filing cabinet. The filing cabinet's keys, that is to say the labels on the front, are strings. So when I ask the filing cabinet to give me the contents of the drawer with the label birth, the contents of that drawer are 1564, and that's what I see. So I can actually do some calculations. So how old was Shakespeare when Shakespeare died? Well, let's take the death date and we'll subtract from that the birth date. Shakespeare was 52. So there are multiple things that I can do with this, and it's a very useful data structure. But before we go on, I just wanted to show you one more thing. So is first in, I can't spell that, in person true? What that tells me is that this dictionary has a drawer whose label is first. Good. Now, let me ask this question. Is 1564 in person? No, it says no, it is not in person. This is a crucial component about asking in and not in with dictionaries. In only refers to the keys of the dictionary. That is to say, in refers only to the labels on the drawers. In and not in do not look at the contents of the drawers. So we're going to have to, if we wanted to look inside the contents of the drawers, we're going to have to do a little bit of finesse later, and we'll figure out how to do that. So is death in person? True. Is money in person? False. Right. So again, dictionaries behave slightly differently in this regard, especially with in and not in. So in another video, I'm going to return to this in the next video, and we'll explore a little bit more. Actually, no, we're not going to be honest. At some point, we will explain how to do that. We need a function first. All right. Promises. All right, that's it for this video. Thanks very much.